Okay, so looking purely at the potential temperature, we can say which water mass is bathing which ocean and what is the direction it's coming from, since potential temperature is a conservative property for all practical purposes. Okay, now what we're going to do next is look at the composition of seawater. Salinity, composition we have covered. Now, in terms of seawater chemistry, what we are interested in is the dissolved concentration, the concentration of the dissolved components, whether that be an element or an ion or a cluster of ions, we don't care. The classical inputs are river, dust, hydrothermal vents, there is air-sea gas exchange, radioactivity, which leads to production of certain elements. A good idea is radon, and biology, essentially the respiration part of biology, where you take organic matter and respire to form dissolved components. The output of elements from seawater is driven by biology dominantly in the form of primary production. Please keep in mind this primary production can be formation of organic matter as well as hard tissue shells. Whenever you write with a chalk, that's an effect of biology on seawater. Whenever you walk on a marble floor, that's an effect of biology on seawater. Every ounce of marble on this planet used to be a dissolved calcium ion and a carbonate ion in seawater. Marine calcium carbonate secreting organisms brought them together, formed calcium carbonate. It got precipitated to the bottom of the ocean, went through a cycle of uh, subduction, compaction, and formed the features that you observe in the modern day. So the output is through biology. Some elements are removed in hydrothermal vents, some elements are added via hydrothermal vents. Air-sea gas exchange can also lead to uh, escape of gases from dissolved in seawater. Radioactivity in the form of decay can lower the concentration. And then there is the orthogenic or the in situ clay formation, the constant reaction that is going on at the bottom of the ocean at a very slow rate, but over such a large area that it is one of the primary drivers of seawater chemistry. So we're going to try and understand the river bit quickly. This is a global map of rivers draining into each ocean basin. I hope the map is visible right now. We need not worry about anything that's happening in the Antarctic. Okay, these are the rivers that's draining into Atlantic. You can see there's a lot of rivers draining into Atlantic. This is the rivers which are draining into the Indian Ocean. Small area, but a lot of water going in there because there is the Himalayas, there is the Indian summer monsoon. So all in all, rivers are always carrying products of chemical weathering with them. This is a nice false color image showing what exactly happens on the planet when there is a weathering reaction. Weathering reaction, chemical weathering happens in presence of carbon dioxide or any acidic gas, whether it be nitrous oxide, sulfur oxide, any gas that can dissolve in water present in the atmosphere and form an acid will lead to a strong chemical reaction. One of the reasons why we are worried about the Taj Mahal is that the industrial sectors in the UP are emitting a lot of nitrous oxides and sulfur oxides, which combined with atmospheric moisture is forming nitric acid, sulfuric acid. Taj Mahal is made out of marble, which is a highly reactive and highly weatherable rock. And so it's dissolving away the, the main structure of the Taj Mahal. So coming back to earth sciences, we are looking at the iron silica mineral, fayalite. It reacts with CO2 to form siderite, FeCO3. What about the products? The products go into solution. So this is a schematic overview of what happens on the continents and how things are transported to the ocean and what happens in the ocean. We are starting with continental silicate rock. You can replace it with continental carbonate rock and simply write CaCO3 or CaMgCO3. Reacts with carbon dioxide to form dissolved ions. These dissolved ions are carried to the ocean, and in the ocean as a river runoff. In the ocean, they partake in biology. Some of them partake in biology, some don't partake in biology, and they're sedimented out. The sediment is then subducted, and the subducted sediment is put under a lot of pressure and temperature, and they reform the rocks. And a part of the dissolved ions undergoes these low temperature clay formation. The CO2 that's coming to the atmosphere and reacting with these rocks are coming in the form of volcanic activity, essentially a degassing from the mantle. Why is this important? This is important because this is a constant cycle which brings material from the deep to the surface and transports material from the surface to the deep. In astrophysics, when people are looking for an exoplanet, a planet that can be habited, can be habitable, the first thing scientists look for is presence of plate tectonics. Plate tectonics is nothing but the, the circulation of the mantle. Remember, when we talked about the heat budget of the planet, we said that there is 43 terawatts of heat coming from the inside of the planet. That's from radioactive decay. So a very old planet will have most of its radioactive elements decayed away. So there won't be much heat left in there. Without heat, you don't have a convection cell. Without a convection cell, you don't have plate tectonics. And without plate tectonics, you don't bring material from the deep interior to the surface. Remember, the surface is a thin veneer. We might think that 10 kilometers, 12 kilometers is a lot of depth, but if you have to sustain life over billions of years, you have to keep recharging the surface reservoir by bringing material from the deep to the surface. So life cannot exist without plate tectonics. And the fact that in the deep ocean, there is the mid-ocean ridge system where you have hydrothermal vent systems is considered the place where life originated on planet Earth. Now, coming back to weathering, these are the simple weathering reactions that we can think about. One is the weathering of the silicate rock, CaSiO3. The other one is the weathering of the calcium carbonate rocks. Calcium carbonate rocks weather easily. We all know that the rate of reaction of a carbonate compound with anything acidic is much faster than that of a silicon oxide bond, because silicon oxide bonds are much stronger than a carbon-oxygen bonds. Within the ocean, biology takes over. They form the shells of calcium carbonate and silicon dioxide, and the subduction takes care of it. In the entire process, CO2 is consumed on the surface, CO2 is produced during calcium carbonate formation, and then again during subduction. So there's a constant cycling of carbon dioxide from the mantle to the surface, from the surface to the ocean, to the ocean to the back to the mantle, and then mantle to the surface. Please keep that in mind. But when we compare river water chemistry to seawater chemistry, the first thing to observe is that in seawater, the major ions are sodium and chlorine, whereas in river water, the major ions are calcium and bicarbonate. There is some amount of magnesium and sulfate, which we also observe in seawater, but chlorine is not a major component. There is a lot of silica in river water. There is not much silica in seawater. We can't even find the silica on the list of elements. There is some chlorine in river water, but most of this chlorine is nothing but dissolution of evaporites and coming back into the ocean. Okay. Now, why is this the case? Why do we find certain elements at a very high concentration in river water, but not in seawater? And we do find sodium and chlorine in very high concentration in seawater, but not in river water. This is purely a function of reactivity and biological utilization of the elements. Chlorine is very low, dissolved chlorine has very low reactivity. Gaseous chlorine is highly reactive, dissolved chlorine is non-reactive. We know for sure all chloride salts are water soluble. As a result, chlorine has a long residence time of seawater, thus chlorine has a very high concentration in seawater. Next lecture, we're going to attack the residence time idea. So this is again, the salt content of seawater. And if we look at the river flux from different continents, what we find is that it's dominated by calcium magnesium bicarbonate. Calcium magnesium bicarbonate. There is little of that dissolved salt pleasant that dominates seawater composition is seen in river water. I'm going to leave you with this, which gives you an overview of the periodic table, elements in the periodic table, and their composition in seawater. The ones in white are in trace. We're looking at something less than 50 picomolar. The ones in light gray is also trace. We are looking at something between 0.5 to 50 nanomolar. Then the darker colors gives you minor, major, and really major components. The really major components are the sodium, magnesium, potassium, calcium, strontium, boron, oxygen. Obviously, water is a big part of it, not dissolved oxygen, but water in the form of H2O, sulfur, chlorine, and bromine. Okay, I'm going to stop here and take some questions if you have any. Do we have any question for this lecture? Okay, if we are good about that, then we'll call it a day. Thank you for joining the class on the 1st, and Happy New Year to all of you again.
Thank you, sir.
Take care. Bye-bye. Bye.